So we are looking at the chapter communication systems now, and as you would all know, it's a pretty informative chapter. There's not a lot of theory involved. In fact, there is a lot of information there, and you are expected to understand how things are working in these topics and work with them. And questions usually will not be very large or complicated. They will just involve you being familiar with those terminologies and those concepts. And mostly such questions people usually ignore and are usually not prepared with. But honestly, in an entrance exam, such questions can get you easy marks, because there's not a lot of manipulation involved in solving such questions. And in this topic, we will be looking at propagation of electromagnetic waves. Then after that, we will move on to the properties of communication channels. And then we'll be looking at modulation and demodulation and antenna properties. And then finally we will end with the
diagram, the components of a basic communication system.
Okay.
So first let's start with propagation of electromagnetic waves. So for this we have three types of propagations.
Right.
One is ground wave.
Okay.
Second is the space wave, and third is the sky wave.
Right.
So I'll show you how this phenomenon takes place.
Okay.
So if this is the Earth's surface, and say this is the sender, some transmitting antenna, and here is the receiver.
Correct.
So what happens in ground wave is the signal that comes from this first transmitter, it gets reflected on the Earth's surface and reaches the receiver.
Correct.
For a space wave, the traveling takes directly from point to point.
Right.
So it's a line of sight communication.
Okay.
And for the sky wave, here we have the Earth's atmosphere. If this is the layer ionosphere, then it goes this way, gets reflected from the ionosphere and reaches the receiver.
Right. So the ionosphere which you would have been familiar with, and sky waves are those waves which actually fall into that category with
they get reflected from the ionosphere.
Right. So those waves are called sky waves, and a lot of people know what ionosphere is simply because of this reason. So those waves which actually work like that are called sky waves. Okay,
next we'll go to a few properties of the ground, space and skywave propagations.
Right.
So first, for the ground wave propagation, you should know that it travels really close to the Earth's surface. That's because it gets reflected from the Earth's surface, so it has to go really close to the surface. And people use low frequency for these waves, that is like 500 kilohertz to 1500 kilohertz basically. And then these waves are also known as medium wave propagation.
Okay. Why low frequency?
Low frequency is because for these waves even low frequency would do, and as you know, frequency, for higher frequency we need more power in the transmitter.
Correct.
So if it can be done with a lower frequency, then we'll prefer that.
Right. Okay.
Then next we move to the space wave propagation. This is the direct interception of signal by antenna. As I already told you before, it's a line of sight communication. So the signal that comes is directly intercepted by an antenna.
Right.
And then it uses 100 megahertz to 220 megahertz. That's slightly higher frequencies than the ground wave propagation. And then the maximum range of this propagation depends on the height of the transmitting antenna.
Right.
So for that, I'll give you a formula. This is D, that is the range of communication. Maximum range depends on root over 2HR, where H is the height of the transmitting antenna and R is the radius of the Earth. So the maximum distance that the signal can travel depends on this formula.
Right.
So some questions might come from this formula in your entrance exams.
Right.
So you are supposed to remember this properly. Then next
it's also very similar to root 2HE and other such formulas.
Yeah, it's pretty similar, but you are supposed to remember this because questions directly come on this formula.
Okay.
In this chapter, most questions are like theory based or formula based. So you need to know this theory and remember the formula, and you'll score easy marks.
Right. And you can see that this is valid for higher frequencies because it has to be mostly transmitted through space, and we'll need higher power for that, and hence higher frequencies. So we'll look at sky waves now.
Next we'll look at skywave propagation. So this is directed towards the sky, reaches the ionosphere, and it is reflected back.
Right.
So the frequencies used are 2 megahertz to 20 megahertz. You're supposed to remember these values because questions might be asked on them. Never know.
Right.
And then the critical frequency is like you are supposed to remember this as well. Maximum frequency that will be reflected by the ionosphere.
Okay.
Because if the frequency is higher than the critical frequency, it will just travel through the ionosphere and not get reflected.
Because the particles, the excited particles in ionosphere cannot
cannot reflect it back.
Right.
The frequency would be so high that it will have too much energy and it will move out of the ionosphere.
Correct.
It will go into space.
Right.
So that we do not require that. We wish that it gets reflected back so that it can be received by.
And that is why you see
receiver.
an intermediate range of frequencies also.
Yeah.
Okay.
And then for this we have the formula FC. FC is for like critical frequency is 9 into root over n max, where n max is the electron density of the ionosphere.
Okay. So we see that it directly depends on the electron density.
Yeah, electron density. If electron density is more, then we can use a higher frequency.
Right.
And then we get a formula for effective refractive index of the ionosphere as well. So mu, which will be the effective refractive index, is equal to mu naught root over 1 minus 81.45 n divided by nu square. Nu square is the frequency that we use in hertz. N is, as I already told you, it's the electron density of the ionosphere.
Right.
Mu naught is the refractive index of free space.
Right.
So basically mu naught equals 1 in most cases.
Right.
So this is these were the properties of the three-wave propagation systems.
Right. In fact, even in the formula mentioned there, you can see that for very high values of mu, there will be less reflection.
Yeah, refractive index will become lower for higher values of mu, and as we all know, if refractive index is low, then the rays won't get reflected back. This is like
so
similar
there will be
to
loss of
total
power.
similar to total internal refraction.
Right.
So if nu is very high, it won't get reflected back.
Okay. So we'll move on to the properties of a communication channel now.
Yeah. So I'll tell you firstly about the bandwidth of a communication channel. So the bandwidth, as you might already know from like your day-to-day life, that it is difference between the highest and lowest frequencies allowed to pass.
Right.
That is, if this is a communication channel and you have different frequencies that are going through, this will be the highest frequency, this is the lowest. So this will be known as the bandwidth.
Right.
That is difference between highest and lowest frequencies. And then the number of channels that can be used is given by total bandwidth of all the channels divided by bandwidth per channel.
Right.
So this will be the number of possible channels in any, like say ground waves or space waves, whatever. So the number of channels would be dependent on the total bandwidth available and divided by bandwidth required per channel.
Right.
So that will give you the number of channels that you can have.
Correct.
Next we move on to another property, that is maximum usable frequency, MUF. So if the sky waves are sent at an angle theta towards the atmosphere, and then the MUF, that is critical frequency, divided by cos theta would give you the MUF.
Right.
FC by cos theta. So this is another formula to find out maximum usable frequency. So next we move on to skip distance. That is another property, and you are supposed to remember this formula because questions might come on this.
What exactly is skip distance though?
Skip distance is a property of this communication channel, and it is given by this formula twice h root over nu minus nu c. This nu c, as we have seen before, is the critical frequency, whole squared minus 1, and here h is the height of the antenna and nu c critical frequency. So this is like a property where this goes into the ionosphere, comes back. So here there will be a skip distance in the receiving antenna. So this you are supposed to like remember this formula because questions come directly based on this formula itself.
Right.
Okay, next we move on to amplitude modulation. So I'll just give you a few properties and some formulae related to amplitude modulation.
Okay.
So first we have the carrier wave equation. So as we all know, the carrier wave equation would be a basic wave equation, that is Ct equals to AC sine omega Ct.
Okay.
So here it is AC will be the amplitude, and this will be the angular frequency multiplied by time. So carrier wave is a sine wave. So here we'll modulate the message signal onto this wave. So this is the original
hence
wave.
the word carrier, because it carries your message.
It does not have the message in itself. So when we'll modulate it with a message signal, there will be a slight change in frequency or amplitude based on the mode of modulation used. So this carrier wave would be modulated with a message signal, so that we get a final wave that will be slightly different. So for the message or modulating signal, we have the equation mt equals to am sine omega mt. So this is another equation of a wave, sine wave itself. So am is the amplitude of this message wave, and sine omega mt is like simply the frequency multiplied by time. So it is also another sine wave, and we can add these two to get the final signal. So here omega m is twice pi fm. As we all know, the frequency multiplied by twice pi gives the angular frequency. So this you get from your basic wave and oscillations chapter. So here after adding this is Cm. So it is like the carrier wave plus the modulating or message wave. So we get AC plus am sine omega t whole multiplied by sine omega ct.
Exactly. So note that this is not just superposition of two waves. It's modulation.
It is modulation.
So you're adding to amplitude, and then there is another sine omega ct term.
So we are adding this. This will give us like the total amplitude, and this will sine omega ct is like again the carrier wave frequency and time. So this will give us the final wave. So after simplifications, these are just different forms. This equation can also be written as this. So we are just making some simplifications, and this is known as the final modulated wave. So here there is one interesting term here, am by AC, that is the amplitude of the signal, modulating signal, divided by amplitude of the carrier wave. Here it is known as the modulation index. So it is basically mu, or sometimes also written as m. So you're not to get confused with mu and m. So it is kept less than equals to 1. So that to avoid distortion, minimize distortion. Distortion like is the introduction of noise. Due to introduction of noise, there is some distortion, or like let's say some difficulties in receiving the signal and getting back the original message.
So basically to remove or to minimize distortion, actually our message amplitude always has to be lesser than the carrier amplitude.
It is kept less than equals to 1, the modulation index. So next we have this again. This equation can also be written as this. So we are just making some few more simplifications to get, like, let's say these two frequencies. So this wave can also be written as this two frequencies, and plus this will be like the original frequency of the carrier wave. So here what we do is we just use our basic trigonometric equations and properties to just manipulate this result, and we get two cos terms here with different frequencies. That
exactly. If you are interested to know how you do it, there will be a sine omega mt term and sine omega ct term, and you can just use those sine a plus b plus
all those trigonometric properties to get these two parts. Here this is the frequency of the original carrier wave. This is the frequency of the carrier wave minus the message wave, and carrier wave plus the message wave. So basically we have three frequencies, like here would be this omega c minus omega m.
So this is when we'll be looking at the spectrum of this signal.
So this will give us like this, say the bandwidth, because this will be of lower frequency. This is the wave, original wave, omega ct. This will be omega c plus omega m.
So what is being shown on screen right now is how the spectrum will look, So a spectrum, is how much energy is there at what frequency.
Let's say that this is the frequency nu, and this will be the amplitude. Here, since this is mu is less than equals to 1, and also we have a half term, so these two frequencies, like the omega c plus omega m, omega c minus omega m, these two will be slightly lesser in amplitude, and this will be like the a sine omega ct. So this will be of a higher magnitude, like amplitude, and the frequencies difference in these two will give us the bandwidth. So this is
We
basically
also call them the sidebands.
Yeah, we
Okay.
call them the sidebands. So this is basically the total bandwidth of amplitude modulated wave, AM waves.
Okay.
So this will give us the total wave equation of the wave of this AM waves.
Right.
So here omega c minus omega m is lower side frequency, and similarly omega c plus omega m would give the higher side frequency. So they are the sideband frequencies. Difference in them will give us the bandwidth.
Right.
So next mu is equal to MA, as I already told you. AM by AC is equal to the E max minus E min, that is maximum voltage of the AM wave minus
Okay.
the minimum voltage divided by E max plus E min.
Okay. Note that E here, meets EMF, and that's why voltage instead of energy.
Yeah.
Otherwise, E and amplitude actually never have a direct relation. It's
Yeah.
always a square relation.
It's voltage will be there. So
Okay.
voltage of the AM wave, so maximum minus minimum divided by maximum plus minimum
Right.
would give us mu.
So this is shown because when you represent amplitudes in terms of voltages, and there is usually no zero voltage transmitted. There's always
Yeah.
a minimum and a maximum voltage transmitted.
Yeah,
So when you write that expression in terms of AM and AC, this is what you arrive at.
Yeah, so we get the modulation index in terms of voltages of the wave,
Right.
which can be related to the voltage of the transmitter itself.
Okay.
So that we can get these voltages fairly easily. So that will give us the modulation index.
Okay.
So next we move on to antenna and their types and properties.
Right.
So first let's see the types. One is the dipole and another is the dish. So dipole antenna, as you might already know, is like one directional, and they transmit radio waves in resonance with omega c, that is in resonance with the
The carrier
frequency
frequency.
of the carrier wave.
Right.
Yeah. Then dish, as you all know, you would have seen in those TV reception dishes and
Right.
all that. So they are used for transmission and reception of ultra high frequency and microwaves.
Right.
So these are like higher frequency waves, and they are used there we use the dish type of antenna, and basically in radar, satellites, TV transmission and all that.
Note that when we say ultra high frequency, they are so high frequencies that we don't usually intend them to get reflected by something.
No, we use them for direct line of sight transmission.
Right. In fact, direct line of sight to even satellites.
Yeah.
Okay.
So satellites also, we send it directly to the satellites, and the satellite might reflect it back, and this can be intercepted by a dish type antenna.
Right.
So next we have the size of the antenna. So one basic thing that you need to remember for the size of the antenna is that it is nearly like of the order of the wavelength. So for higher wavelengths we need a bigger antenna.
Right.
So here I'll talk about two types of antenna. One is the Hertz antenna, also known as half wave antenna,
Correct.
because the length of this antenna, let's say the aperture or the length would be equal to lambda by 2. Lambda is the wavelength.
Right.
And next we have the Marconi antenna, known as quarter wave antenna.
And if you remember, Marconi is the person who invented the radio.
Yeah, invented the radio.
Right.
And it is L equals to lambda by 4. Lambda is the wavelength, divide by 4, hence the name quarter wave.
Okay.
So these are two types of antenna. We can have different sizes as well.
Right.
So for that we always need to remember it is like of the order of the wavelength.
Right. As you can see here, the size here is lambda by 2 and lambda by 4. So it's very easy to guess that most antennas will have
Yeah,
comparable
it will
sizes.
have within like lambda by 2 to lambda by 4. Most
Okay.
antennas will have that length.
Okay.
So there, if the wavelength is too high, for example for radio waves and long waves, the wavelength is more, so we need a bigger antenna.
Right.
But for microwaves and high frequency waves, the antenna can be made smaller.
Okay.
And then we have the power radiated by an antenna. So power is directly proportional to 1 by lambda square, whole square.
Okay.
So here it is inversely proportional to the square of the wavelength. So the bigger wavelength we have, the lesser power would be radiated.
Okay.
So like from this you can directly infer that for higher frequencies more power would be like emitted.
Right. Note that we arrived. We can't tell you at this point of time without talking about antennas too much about how we arrive at this expression, but keep in mind that it would also be the matter of the size of the antenna, which we would write in terms of lambda, and that is how you would possibly get at this expression.
Yeah, so for bigger lambda we need bigger antenna, and then there is it depends on the size as well as the wavelength and all that stuff.
Right.
So for like basically for now you should remember that if the wavelength is bigger, the power radiated by the antenna would be like smaller.
Right.
So if the power radiated is smaller, the range would be lesser.
Okay.
And for higher frequencies we have more power, and the range would be more.
Right.